Okay, 3, 2, 1, here we go. This is the last lesson of chapter 7. So as we kind of look at where we're at, we need to get through as quickly as we can. We need to get through chapter 7 so that we can get to chapter 8. So your test will be on chapter 7 and chapter 8. So tomorrow, you're going to have a day to work on tomorrow's assignment. So the problem is that as we put together these pieces that we talked about a couple days ago, yesterday and today, my concern is that you're not going to know what to do when, okay? And so tomorrow's assignment is, you'll be looking at a problem and you'll be trying to say, well, how is this different than the problem after it? And so trying to figure that out will be the important part. So if you haven't done either of your previous 2 assignments yet, then you might struggle to come up with what we're doing tomorrow. I do have all 3 answer keys, meaning the one for today, all ready to go as well. And so we should be good to go there, okay? A couple changes on today's lesson, but not too many. Let's just start. I understand what makes... we're going to wait for Danny. Here's Danny. Everybody say hi, Danny.
Hi, Danny.
Oh, they like you so much.
Most obvious. It's so fun.
Okay, here we go. Suppose that the average height of an adult female in the United States is 66 inches with a standard deviation of 2.3 inches. If you were to select an adult female at random, what is the chance that she would be taller than 68 inches? So we've done this exact kind of problem before, where we've said that this is exactly 66, and we're wondering the chance that she is taller than 68. Somebody remember how I'm going to set this up here? Yep.
You do 68 minus 66 over 2.3.
Yep, that's how I compute my z-score, correct? Because we've said that heights are normally distributed, and so we could go ahead and use our z-score in our probability piece. I could go ahead over to my statistics template. I really like using this piece. If you want to bring yours up, you can. If you don't, that's up to you. But I am going to use this today a few times. And if you notice, if yours pops up with numbers, that's because every time I type, that's what yours is going to pop up with when you first make a copy of it. Unless you just keep a copy for yourself, open up all the time. I type in 2.3, and I get those following values. So everybody should be clear that within this situation, that when you do this, you get a value of 0.8077. That is the area to the left. I'm wondering the probability that she would be greater than 68 inches. That is the probability to the right. How do I figure that out?
1 minus 0.80.
1 minus 0.8077, and I get 0.1923. Old hat, we've done before, right? So what's different about today? Well, today it says that we will be sampling means. So yesterday we were sampling proportions. So the idea was, suppose we sample a group of people together, what is the chance that their job approval of the president is, say, greater than 43% if overall we say it's 41%? So today we're going to sample a mean. So here's where it makes the question different. This is what you have to understand for tomorrow's assignment as well as for the test. If you don't get this, you're not going to know what to do when. Because if you come to me on the test, say, which one do I use? I will say, I'm not telling you. Everybody get that? If you were to randomly select, here it's just one individual, right? That she would be taller than 68 inches. One individual. Whereas in this situation, we're randomly selecting 120 females. What is the chance that their mean height? Okay? So we grab a bunch of girls, and we're going to look at their average height as opposed to one person. Everybody get the difference? So we have a different distribution in this situation, okay? And so we need to calculate the sampling distribution for mean, both the mean and the standard deviation. And here's how I'm going to calculate that for you. I wrote down some shorthand and stuff. But if you collect a sample of a mean, so suppose we take a sample of a mean and we calculate that. We do one sample and the mean is 65 inches. And we do another sample of the mean, and the mean is 67 inches. And we do another sample of the mean, and the mean is 64 inches. Okay?
I was envisioning Andrew.
Okay? And we do it over and over again. As we add those up, that will be the mean of the total. Okay? As you sample these over and over again and you get good numbers, these means are going to become very close to each other, meaning that the mean of the total will be a mean plus a mean plus a mean. And we're going to add up n of those means. So if we add up n of those means, the total computation comes to n times mu. That's what they're all going to add up to. Now we can do a similar situation here with standard deviation. If you remember, when we looked at standard deviation, combined variables, we actually looked at combining the variance. So the variance, we would take one variance, we'd add it to another variance, we would add it to another variance, so on and so forth. Those variances would be different each time. However, as you add up more and more of them, they would start to become the same. So the sum of the total variance would be just the variance plus the variance plus the variance. And we would add up n of those. So what would that add up to? If I add up n variances, it would add up to, yeah.
Is the last one supposed to be 3?
Oh, sorry about that. It would add up to n times sigma squared. Okay. Do you remember what we did with the variance in order to compute the standard deviation? So if the variance is sigma squared, what did we do to compute the standard deviation? We took the square root, okay? So if I square root this, okay, I'm going to use my property of square roots. I have the standard deviation is going to be equal to, and here I'm going to separate this into two parts. The square root of n times the square root of the standard deviation squared, using some algebra there. I can't simplify the root of n, but what is the square root of sigma squared? Just sigma. So we added up a bunch of these things. How many did we add up?
120.
N. We added up n, right? And when you take an average, you take you add up a bunch of things and then you divide it by the number of things you added up, right? So all we're going to do in this situation is to figure out the new mean. We simply take n times the mean divided by n, because we added up n things. And what's that going to give me? It's going to give me the mean. So in this question, when it says, if you were to randomly select 120 females at random, what is the chance that their mean heights would be taller than 50 or 68 inches? If you're looking at the mean of x bar, or the mean of the mean, we simply choose the mean that was given to us originally. And what is the mean of the females for their heights? 66. It's not quite the same for the standard deviation. Look what happens for the standard deviation. Again, we have n of these, so as we find the average, we need to divide by n. So the standard deviation is going to be equal to the square root of n times sigma divided by n. Now, those of you who've taken college algebra and calculus, you're going to see this quite quickly. Others, if you've just taken algebra 2, you might not see this as quickly, but I'll write it out. This is n to the 1/2 power. That's what the square root means. Times sigma divided by n to the first power. And what do we do to the exponents when they have common bases? What do we do to those exponents? We subtract them. And 1 minus 1/2 is just 1/2. And so you get sigma over n to the 1/2. Or in other words, sigma over the root of n. And so this is our standard deviation when we're talking about the mean of a sample. Okay? So we have the mean of a sample. You have to take the standard deviation and divide it by the root of n. So up here, we get to use mu is equal to 66. But our standard deviation, there we take our standard deviation lifted above, which is 2.3, and we divide it by the root of n. N stands for our population. What is our population? 120. So we use that in order to determine our standard deviation for this problem. So go ahead on your calculator, take 2.3 and divide it by the root of 120. Please make sure you come up with the same thing that we have up on the board as well. Lily, what'd you get? 0.20996. So if we would like to be able to find, okay, the chance that the mean height is taller than 68 inches, what we will do is we'll take that 68 minus 66, but this time we're going to divide it by 0.20996. I'm going to go ahead and grab my information here. Notice how those other numbers are the same. And what did we have, Lily? 0.20996?
Yeah.
Look at our z-score and look at our percentile. Talk to the person next to you. What does that mean about this problem? Go, talk.
I don't take it.
The dart game has some more.
You just find people that are.
Let's pretend that we're doing statistics. What do those numbers mean? Try the percentile.
Okay, folks, so here's what it means, in case you haven't seen it yet. I'll draw it out for you here, okay? So what we have is this, okay? 66 is the mean, and we're seeing where does 68 fall, okay? It's saying that if you have 68, it says that 100% of the data lies to that side. So what percent of the data lies to that side? None. So what is the chance that you actually select 120 girls at random and their average height is 68? None. It ain't going to happen. It's not going to happen. Okay? So you can see that when we are doing a mean, the standard deviation changes. And when the standard deviation changes like it does, it becomes much smaller. The probability definitely reduces significantly. I made these problems ahead of time, and as I then went through them, there were a couple that I didn't like. And this first one here, we're going to change this to a plus or minus 2. And down here, we're also going to change this to a plus or minus 2. the average life expectancy of a man is 75.8 years with a standard deviation of 14.8. That's approximate. We really struggled to find this standard deviation. I kind of made one up based off of some things I researched. But it says choose a random sample of 100 men. What is the sampling distribution? When we ask for sampling distribution, that means we are looking for the mean and we are looking for the standard deviation. We did both of those in the previous problem. See if on your own or with a partner, you can come up with the mean for X bar and the standard deviation for X bar. Go ahead.
And this is 50, that would be 14, so that's the square root of 100. Or 14.8. So that's calculate. We need me and Cooper, my partner. I do.
Fortunately, you all can see that you don't need a calculator because you know that the square root of 100 is 10. So you can simply just move the decimal point one spot, 1.48. Okay. Is everybody clear where I grabbed the mean? That's easy, right? Just grab the mean from the previous spot. But the standard deviation, you got to take it and divide by the square root of the population. So let's go to the next part. Suppose we were to grab 100 men, okay? And we were to look at their average life expectancy. I guess we're probably not grabbing men that are alive. We're probably grabbing men that died, right? To figure out, how long did they live? You know what I mean? Okay. So what is the probability that the mean, okay, the average, is within plus or minus 2 of the average that we have here? So it says, what is the probability that the mean life expectancy of 100 men is between plus or minus 2 of the mean? So if we take that 75.8 and we add or subtract 2 to it, okay, we would be at 73.8 and we'd be at 77.8. Are we okay with that? So we're going to do 2 tests for each of these, or for one for each one for a total of 2. We'll do 73.8 minus 75.8 over our standard deviation of 1.48. And then we will do 77.8 minus 75.8 divided by 1.48. If you want to use your computer, go ahead. If you want to use your sheet of paper and stuff, go ahead. But please come up with the 2 p-values, the probability values for each of those, okay? Go ahead. Take about a minute.
And
Sir?
so on a test, how are you, like, what in the problem tells you need to do this and do the other standard deviations?
How do you know, how do you know that you are doing the 14.8 over the square root? The fact that it says, okay, what is the probability that the mean life expectancy of many men? If it was just one person,
Oh, yeah.
and it was asking about their height, then we wouldn't do that. But we're sampling and we're looking at the average of that sample. You see that?
Yeah. And that's the same thing with positive. I don't. Yeah. I mean, if we turned it cheaper. I think so.
Did everybody come up with a negative 1.35 and a positive 1.35? And if you notice, what's nice about your computer is it does convert it perfectly to these probability, which is a 0.08 and a 0.91. So the question is, what is the probability that it's between those? What would I then do to those probabilities? We would subtract them. So we would take the 0.9117 and we would subtract 0.08829. And out of that, I come up with a 0.8234.
Inspirational.
We're going to do the exact same thing, but we're going to change one part of it. Instead of selecting 100 men, we're going to select 1,000 men. What do you think is going to then happen to our overall probability? Do you think we're going to get a number that's going to make us less certain, meaning like 0.6 or 0.5? Or do you think we're going to end up being more certain, like say 0.9 or 0.95? What do you think?
More certain.
You confident about that?
Not really.
But you made a guess. The star quality of taking a risk. A lot of people are afraid to do it. You guys go ahead, do the same exact procedure, except this time you're using 1,000. So the mean will stay the same, but what will change? Standard deviation. So you're going to get a new standard deviation.
I got some for you. Where's the R? Yeah, I know. Oh my God. I know. You can say that again. Maybe something worse.
Were people able to come up with a z-score of about 4? Or a -4, and then a z-score of about +4? Which is a little bit more than that, right? And so that translates to basically no chance that it's less than that, and basically 100% chance it's less than that. So what does that tell us? What is the chance that we select a group of 1,000 where the mean is somewhere between 73.8 and 75.8? It is almost absolutely certain or not certain? Certain. We're going to build on this. We're kind of planting the seed in your brain right now, because do you think in statistics we like to be almost certain, or do you think we like to be absolutely certain? So in order to be absolutely certain, we selected 1,000 instead of 100. Does that make sense? So why not just select 1,000,000? That's a lot of work, isn't it? Absolutely. So we would like to know, kind of like, what's the smallest number that we could grab in order to be absolutely certain? You get my point? Because it takes time and money to survey people, and that's what we'd like to find out. Okay, last 2 examples on the back. A local meat market sells ground beef in 5-pound packages, which is the same as 80-ounce packages. Somebody can you tell me how many ounces are in 1 pound? Anybody know? There are 16 ounces in 1 pound. So if I simply take 16 and multiply by 5, I get 80, okay? We like to buy our ground beef from Fairway. They cut up different roasts and steaks, and then whatever they cut up that day, that's where we get our ground beef from. We really like it. However, they actually find that the mean of the packages has been 81.5 ounces with a standard deviation of 0.9, okay? So as you look at this problem here, a mean of 81.5, standard deviation 0.9, why do you think there's actually more than 80? You got people that are packing up. You think people are more likely to complain if they get less than 80 or more than 80? Yeah, they don't want less, right? They don't want to be short-handed. So they're finding that they put a little bit more in. What is the probability that a random customer receives a package of ground beef that is less than 80 ounces? And then, what is the probability that a group of 40 randomly selected has a mean less than 80 ounces? Can you see the difference between the two questions here, what you're being asked? The first one is about a single individual. So what do I set up? Yeah. And so in this situation, the mean is equal to, this is the parameter, the mean is actually equal to our 81.5. And that is what we choose to use as our statistic in here, is 81.5. What's the probability that it's greater than 80? 80 is what we are testing. That's our observation. And we're going to divide that by what? 0.9. That was super simple, wasn't it? Okay, we just grab the information that's given. This is something we did back in chapter 1. And when we do this, we come up with a negative 1.667. Oh boy, I did it. Sorry. I was going to write 0.666, but that's like Satan, right? So it's like, you know, I chose 67 over Satan today. All right, there we go. Okay. And if you look at this conversion to a percentile, it converts to 0.04779. Okay? So that means there's only about a 4.7% chance that somebody gets less than 80 ounces. So for the most part, they're doing a pretty good job, right? Every once in a while, somebody might get less than 80, but not a lot. This is different. What's the probability that a group of 40 randomly selected packages has a mean less than 80 ounces? Go ahead, try this one on your own. Try that one on your own. Already did it?
Yeah.
Consensus number 1.
Go quick ones, please.
It says in the seasons.
Do you know the Z-score sheet?
I think I do.
I think I drew right away on this.
Let's say
Did I do it right?
Forget it.
Is it not?
80.1, 81.5. That makes sense. And then it's, so it's 80 minus 80. 40. 0.9. It's 40, no? Yes. Yes. Yep. Okay. Was it 9 and 0.9? 0.1, 0.2. Yeah.
Because I said
Sorry,
there.
Let's do that.
Did people come up with their standard deviation of 0.142? Did you get a z-score of about negative 10? So what that means, again, is if we're here and this is 81.5, then this, 80 ends up being right over here, okay? Negative 10 standard deviations away. That means that 0% of the data is there and 100% of the data is over here. So what is the chance that they select 40 at random where the average is less than 80? Just about no percent. So while they know that every once in a while, they're sending out a package that's a little bit less, if you take a grouping, they're sitting pretty good. They're pretty happy about that. Okay? We can spend 2 or 3 days on the central limit theorem. We're going to spend 2 minutes here. Okay? Central limit theorem is pretty cool in this situation. It allows us to do something very unique, and that is this. We've talked about different distributions, and we really like this first distribution, which is normal. We love normal distributions. They're easy to work with. We have formulas for them. But every once in a while we get something that's not so normal and it's skewed one direction, right? That creates problems. We haven't talked yet about how do we do this stuff if we have a skewed distribution. That's going to be next week. You can actually have a uniform distribution where all things are equally likely. You could have something that makes a bimodal distribution or having a double peak. For example, suppose we were to look at the heights of men and women in this class. Without a doubt, we would get a peak for the women's height and a peak for the men's height. Okay? Here's the cool thing. And this is what the central limit theorem says. It doesn't matter what the shape of the distribution from which you sample the mean. Okay? This is not the case for proportions. This is not the case for everything. But when you're sampling a mean, it doesn't matter what the distribution is that you're pulling the mean from. As you take many samples, the distribution of the mean will be normal. And so what that tells us is if we have a distribution for which we're pulling a sample, it doesn't matter where it's normal, skewed, uniform, or double peaked, it will, when we look at the distribution of the mean, it will become back to normal. And that's really good news for us. So, our last example. The average household income in the United States is approximately $72,000 with a standard deviation of 18,000. Did you expect that to be higher or lower?
Lower.
Lower? Okay. It was 5 years ago. It was about 68. I added 4,000 for inflation. And it is heavily skewed to the right, meaning that you have people making 30, 40, 50, 60, 70,000, but then you have other people who are making 100, 200, 300, $4,000, $400,000 a year. You get how it's skewed to the right? Very much pushed one direction. It says this. Can we calculate the probability that a household selected at random has an income greater than $100,000? Why or why not? And the answer is no. And here's the reason why. The distribution is not normal. So we can't use our fancy little z equals x minus mu divided by sigma because the distribution is not normal. It's heavily skewed. However, we can sample a mean. It says as follows. Suppose we want to know the probability that 60 households selected at random have an average income of greater than $100,000. We're gonna change this because I did the numbers and they don't work out well at all. We're gonna change that to 6, and we're gonna change this to 80,000. It doesn't matter that our original distribution is skewed because we are sampling a mean. It will become normal. See if you can calculate this one on your own. Go ahead. Slowly trying to write the work down behind you. Did you come up with 0.8618? Is that my answer? We're wanting the probability that's greater than, so therefore we subtract 1. So 1 minus the 0.8618 should be equal to 0.1392, I believe. Is that what we got? Very good.
How do you use this number?
What's that?
No,
And so we need to change the last two numbers. This isn't going to work here. We're going to change the 600 to 60. And we're going to ask not between 60,000 and 80,000, but rather between $70,000 and $75,000. This one does not end up becoming almost absolutely certain or not certain. Go ahead and see if you can do that calculation. I will hand out your assignment. We'll go. So I changed that number to be 6.
Oh, okay.
So I went through the problems this morning to see if they would work out, and they really didn't. We had way too many absolutely certain or not certain situations.
You guys kind of ready to go? Go.
Again, tomorrow I will not have any instruction. The goal will be that you complete tomorrow's assignment in class. We need to kind of put different pieces together and see if you know what you're doing when. Do you know what you're doing when? Otherwise, I'm afraid that the test would go poorly. Our schedule will be as follows. We will have a lesson on Monday, Tuesday, and Wednesday next week. We will finish up our confidence intervals, and we'll do something on Thursday. Friday, you will have time to work on your study guide, and then the Monday before, you will work on a study guide, and then you will test the Tuesday before Thanksgiving. You will test the Tuesday before Thanksgiving. So you can check. Can anybody else confirm a 0.7069? And that is your answer. I'll write the work on the board in case somebody's watching the video.
What did you get for student deviation? Yeah. Your student six? Oh. Your student deviation is you have to redo your new number.
And do you gotta be called your alter ego?
What?
You gotta be called by your alter ego.
Hi.
Grave.
I don't have it made yet, so I have to give it to you. Wait, you're gone from today until next Friday, you're gone from and next Friday. Okay. Yeah, I'll get you on Monday. Yeah. Yeah, no big deal. We're just doing a little calculus.
I'll try to keep up with the calc as much as I can and be ready for
Yeah, good luck.
probably.
I'm sure you'll do great. So you just didn't recalculate the standard deviation?
Guns, get ready for those bars. We're gonna beat
Maybe. So all of our work should be done by tomorrow.
I'm not saying that it all should be done, but like you should have a general idea. Like if people haven't done anything, then when they get to tomorrow, they're gonna be like, I don't know what I'm doing.